In this lesson, we're going to learn some shortcuts because long division is very time consuming. But if we arrange its results like this, and we've called this standard form so far, then it gives us two shortcuts that we can use to find factors and remainders more quickly. And we can use these, but only if the divisor is a polynomial with a degree of 1. In other words, a linear polynomial, something like x plus 3 or 5x minus 1 or something like that. So how does it work? Well, if we let the divisor be x plus or minus something, now for convention here we're saying let's always make it be x minus something, and here we're calling it alpha, then we can rearrange this standard form here and say that the polynomial must be equal to the divisor, which we've defined, multiplied by the quotient plus the remainder. Now, the remainder here must be a constant or it must be 0. How do we know this? Well, because we've already learned that the remainder has to have a degree that is lower than the divisor. And so if we've said by definition that the divisor is only going to be linear and have a degree of 1, well, that pretty much dictates that the remainder must have a degree of 0 or no degree at all. So it needs to be a constant or 0. So now we can say, all right, well, we've just created a situation where we've got a nice simple factor here. What can we do with it? Well, if we let x equal alpha, then we can say that we're finding p of alpha. In other words, we're just subbing alpha in, whatever that number is, into our polynomial. But we can also sub it in to this whole side. And the beauty of doing that is that the first section here, which we've kind of created with this trick, is going to be alpha minus alpha, which is 0. And when that multiplies by the quotient, that whole section is going to be 0. So it will just disappear. So then we can say that p of alpha is going to equal r of alpha, which we've got down here. So this forms the basis of the remainder theorem. So let's write a nice neat heading, the remainder theorem, and write this theorem in an important looking box. The remainder, when we divide some polynomial by x minus alpha, is p of alpha. So how do we use this? Well, we need to always be careful to know what alpha actually is, because it's going to be the thing that we've subtracted from x. In other words, it's going to be the actual 0 of that polynomial. So find the remainder when this polynomial is divided by x minus 2. Well, in this case, alpha is 2. So if alpha is 2, then we just need to find p of 2. And that means subbing 2 into this polynomial. So we've got 3 multiplied by 2 to the power of 4, that's 3 16s, which is 48, minus 4 times, what's that, 2 cubed is 8, 4 8s are 32, plus 4 2s minus 8. So these two are going to disappear each other and I'm left with 16. So I can see that the remainder is 16 without even having to carry out that long division. Isn't that great? Now let's make sense of the factor theorem, which is closely related. We've just learned that if we take some polynomial p of x and we divide it by x minus alpha, then p of alpha will give us the remainder. Now, if p of alpha is 0, and in this case alpha has to be a constant that's not actually 0, then what we found is that there is no remainder. So that means that x minus alpha must have actually been a factor of our original polynomial. So that's the factor theorem. Let's put a big box around it. Now, an example here. Let's show that x minus 3 is a factor of this polynomial, but x plus 1 is not. Then we need to fully factorise this polynomial. Now, you can work out, well, let's start by looking at what we're going to need here. We need to work out p of 3, and we need to work out p of negative 1. So p of 3, we're going to get 3 cubed, which is 27, minus 2 9s, which is 18, plus 3 minus 12. So all of that gives me 9, that gives me 0. Now it said show that. x minus 3 is a factor. So this is some working that I can show. If I do the whole thing on my calculator and just say, well, it equals 0, they might be like, yeah, you knew that though. So I sort of like this setting out of working when you're asked a show that question. So I'd say, therefore, x minus 3 is a factor. Be really clear with a show that question that you've really come up with it. Now if we take p of negative 1, we need to cube negative 1, that's negative 1. Negative 1 squared is 1, so we get minus 2 there. Minus 1, minus 12. And all of that comes to negative 16, which is not equal to 0. So I'd say, therefore, x plus 1 is not a factor. Now, the other part of the question says to fully factorize this. So what we've just learned is that this one is a factor. So this is equal to that multiplied by something. What is it? Let's do some long division to find out. So that's always a good backup. So we need to do x cubed minus 2x squared plus x minus 12. And we're going to divide that by x minus 3. So our first term here will be x squared. We should be getting quite good at this now. And we've got minus 3x squared here. Minus 2 minus minus 3 is plus 1. So I have x squared plus x. And that gives me an x here. X squared minus 3x there. And now I've got 1 minus minus 3, which is 1 plus 3, or 4 x's. I can bring down my minus 12. And that gives me plus 4 here. And that will give me that. And minus 12 there. And you can see that my remainder is 0. So that tells me that it goes exactly, which is what I was expecting. If this really is a factor of this, then we should get an answer and no leftovers. So make sure that that is what you get. So then, fully factorized, we could say that all of that is equal to x minus 3, x squared plus x plus 4. Now at this point we want to just check whether or not we can actually factorize that a little bit further. A way to check, look at the discriminant. B squared is 1, minus 4ac is going to be minus 16. The discriminant is negative here, so there's no solutions to this if I was to let it equal 0. So that tells me that it's as good as it gets and I am finished.